Okay, we're back for section 9.2. Now here we're going to be looking at what we do with our central angles and some things about our naming and measuring arcs. So in 9.1, we did go over some of that vocabulary, and the one that we're going to need today is that central angle vocabulary. So what we described in 9.1 of the central angle is an angle whose vertex is the center of a circle and the sides are two radii of the circle. And our central angle gives us some information about our arcs. And our arcs are really a main component of this whole unit. So arcs are crucial. If we don't understand arcs, we are not going to succeed in this unit or chapter. So an arc is simply a fraction of a circle's circumference. So we're going to think about the circumference, and that's something you've done before. And then we're going to take a fraction of it, measure in degrees. Okay. Now the measure is given by that corresponding central angle. So it seems a little funny at this point that if an arc is a fraction of a circle's circumference, why is it measured in degrees instead of as a fraction of the circumference? And that is because we have both an arc measure and an arc length that we are going to talk about in this unit. So right now we're focused on arc measure, which is in degrees. I can't spell it right or anything obviously today. I seem to be out of it. But it's definitely measured in degrees for now. And that is one of the hardest things to understand about circles, because not only are the names very similar, their actions are very similar, what they imply are very similar, but the answers are not. An arc measure is a degree measure, an arc length is a linear measure. They will look completely different, even if they are telling us very similar kinds of information. Now we do classify our arcs, and in other words, we also name our arcs based off of their measures. So minor arcs, these are circular arcs with a measure between 0, they have to be greater than 0. I'm just going to put X as my arc, and they have to be less than 180 degrees. So that's not quite like what we had with our angles. When we talk about acute, right, obtuse, and reflex angles, we had the 90-degree cutoffs. We did 0 to 90, we had exactly 90, we had 90 to 180, and we had exactly 180. And we also had over 180 if we went into reflex. Similar in concept, we're going to have these cutoffs to classify them, but the measurements we use to classify them are different. Okay, so 0 to 180 is a minor arc. A major arc is 180 degrees to 360 degrees. And a semicircle is exactly 180 degrees. Their measurements matter in classification, or classifications matter for measurements. And then how do we know which is which? Our naming conventions also help us. So a minor arc is named by just the endpoints. So if our endpoints are A and B, we would say AB. And similar to our segments had a bar, lines had a line, rays had a ray. So very similar to all of that, arcs have an arc, a little curve. Now, the difference now with a major arc is a major arc has to give you more than just the endpoints, because oftentimes those endpoints don't tell you which direction to go around the circle with the major arc. So we need 3. So if we're going from A to B, but I need to pass through point C to get there, so this would be A, C, B, and that tells me that I'm starting at A and I'm ending at B, but I have to go through point C to get to B, where the other way around to B might be shorter. This is telling me I'm taking the long path. And then a semicircle here it's kind of in between, but we name it like a major arc. Use same naming as major arc. So again, 3 letters. So what this means is if it's just 2 letters, you know right away it's a minor arc. Your measurement needs to be between 0 and 180. If you're using 2 letters and you get 250, something's not right. Either your measure's off or your name is off. And it depends on which one was given and which one you came up with. And vice versa. If you were given 3 letters and you came up with a 30-degree angle, you did the wrong direction around the circle. Something's not right. Use these names and the measurements to help you verify you're going the right way. So let's go ahead and just jump into this example. We are classifying each arc as minor, major, or semi. Then finding the measure of circle C, where AB is a diameter. So they're specifying that's a diameter. We don't have to guess that it's straight through. Now, AD, 2 letters. 2 letters tells me right away this is a minor arc. If the other 2 are both 3 letters, I can't jump right into major or semicircle until I take a deeper look. But I can start anytime there's 2 letters and say that is minor. I know that's minor and I'm good to go. Okay. So minor arc from A to D, that means I'm starting at point A and I'm taking the shortest path possible to point D. And again, arc measures are the angle of that corresponding central angle. So in this case, if I look at it as like a slice of the pie, this is 65 degrees. Okay, we should remember that a circle is 360. If we don't by now, that's something you probably want to write down. Full circle is 360. Straight line is still 180. And we're going to need to do some of that math here. Let's go ahead and fill in what we don't know before we move on. So again, if AB, right here, segment-wise, is a diameter, that means it's a straight line. That means that this angle right here is 180 degrees. And that means this one is 180 minus 65, which is 115. And if I were to add up 180, 115, and 65, I should get 360 degrees total, which is what I want in a full circle. So there may be times that you find it easier just to figure out what all those missing measurements are before you even start answering these questions. So now, I have these 3 measurements. One was given, I found the others. I already found AD was minor and it was 65. Next it wants ABD. Okay, so ABD means I'm starting at A, I'm ending at D, but this time I have to pass through B on the way there. So this is just the opposite of what I did before. I'm going the long way from A to D. My tracing skills obviously need improvement. Now I can add the 180 to the 115 since I already know both of those. Or if I hadn't done that, I could take the 360 of the full circle minus the 65. And this is going to be a major arc. I went further than 180. So let's start by saying it's major. And then we can say this is 360 minus 65, which is 295 degrees. So that's a pretty large angle. And that's the same. 180 plus 115 is also 295. So again, it doesn't matter which way we approached it. And then finally, arc ADB. So we're starting at A, we're ending at B. Well, if B is a diameter, that means that this is going to be a semicircle anyway. Doesn't matter which way we go about it. If those two endpoints are the endpoints of a diameter, this is going to be a semicircle. And if it's a semicircle, unless I've forgotten that a semicircle is 180, I don't even need to go through all of this. That's 180 degrees. Now, why does this matter? Can we make this useful? And yes. Can we use an arc measure to determine a percentage, such as in a pie chart? And absolutely. And if we can use it to find a percentage, then there's a good chance we can actually use it in more applications than that. So here we have a brief example where we have been given arc measures. Why we were given arc measures instead of the percentages in the first place doesn't make a lot of sense to me, other than it's a geometry question. But we can. So here, this survey asks people how many minutes they spend brushing their teeth each morning. The pie chart below shows the results. Answer the following questions. So here in our pie chart, we see that we have several brush for only 1 minute, several brush for 2 minutes, quite a few maybe brush for 3, and a small select few brush for 4. Okay. And according to this pie chart, nobody brushes for less than a minute, nobody brushes for more than 4 minutes. Everybody brushes 1, 2, 3, or 4 minutes. And if you don't know or don't remember, the recommended, I think it's the ADA, American Dental Association, is 2 minutes. So, what percentage of those surveyed brush for more than the recommended 2 minutes? So more than, that means we're not including those that only brush 2 minutes. We're looking at the 3 minutes plus the 4 minutes. So to calculate this, we need to add those degree measures. So we're going to add 13 degrees for the 4 minutes plus the 82 degrees for the 3 minutes, because we can add arc measures and we get that this is 95 degrees. So 95 degrees of our survey brushed for more than 2 minutes. How do we turn that into a percentage? Well, percentages are out of the whole, essentially. We're trying to take it out of a percent, means per 100, but it's out of a whole. So this means we have to divide it by the total number of degrees in our circle. So 95 degrees there, divided by 360 degrees in the full circle, let's see what that gets. That gives us no degrees anymore. Our symbols won't change. 95 divided by 360 is, so I'm going to set this right here so you can see, 0.2638 repeating. Now, to convert this to a percentage, we have to move our decimal 2 places to the right. So this is about 26.3 26.4%. About 26.4% of those surveyed brushed for more than 2 minutes. That's a little more than a fourth of the people surveyed brushed for more than the recommended time. It's not too bad. So now in our next one, if 150 people were surveyed, how many people in the survey group only spend 1 minute brushing their teeth? So how many are doing just a quick brush and saying that's good enough? And we're going to round this to the nearest whole person because it's not going to turn out exact. So here we have to start by figuring out what percentage. What percentage? So 145 degrees over 360 degrees is going to tell us our decimal. So 145 divided by 360 is 0.4027 repeating. And now we typically want to multiply this number without converting it. So 0.4027 repeating times the people surveyed will give me 60.416 repeating. I didn't do any rounding before I plugged these in. And we are told to round to the nearest whole person. Now, nearest whole person is going to actually round down, and that's fine in this case. If you want to round up because you say this is too much, I understand, but make sure you're clear. So this means about 60 people only brush their teeth for about 1 minute out of this 150 survey. So again, this is one of those nice things that we can do with this if we know those arc measures. We can figure out different applications with it using our pie charts and other information. Now, we are also going to be faced with what does it mean for our circles to be congruent versus similar? What does this mean for us? How can we use it? Is it even useful? And circles are unique. Unique isn't bad. Unique just means it's different. Since the circumference and area of circles are both dependent on the radius. Again, I have in here diameter too, because some of us know our circumference based on diameter, but diameter and radius are just half or double. We can do everything based off of the radius. So that means that determining our congruence and similarity, it all comes down to the radius. Okay. Now, why is that important? That's important because it's one piece of information we have to look at to determine if our circles are congruent, first of all, and then because that's the only thing that really sets them apart, all circles are going to be similar because all of the radii can be adjusted by a scale factor. Every single radius can be gotten to one another by some scale factor. Circles are congruent if and only if they have congruent radii. That means if I have two circles and the radius of the first circle is 3 inches and the radius of the second circle is 3 inches, then boom, my circles are congruent. But if the radius of my first circle is 3 inches and the radius of my second circle is 3 centimeters, they are absolutely not congruent, and there's no possible way for them to be congruent. They have to have the same radii. All circles are similar because even that one that has a radius of 3 inches and that one that has a radius of 3 centimeters, we can find some scale factor that will scale one up or down to match the other. Now, what does this mean for our arc measures, unfortunately, it does add a level of difficulty to our arc measures. Since our arc measures are given by central angles, and those central angles go from 0 to 360, that doesn't change based off of the size of the radius. We do have to pay attention to the radii before we can determine congruence. So two arcs with the same measure, important, very important, are congruent if and only if they are part of the same circle, which is guaranteed to have the same radius, or congruent circles, or from congruent circles, which again have the same radius. All comes down to the radius. And that's what we're looking at here. So we have to use our information that really based on that radius to determine if these are the same. So if I look at arc measure of HE, that central angle is 110 degrees. Now GF is also 110 degrees. So if we look at just the arc measure, we are going to be very tempted to say that yes, they are congruent, but they're not. HE is not congruent to GF because the radius, let's call this radius 1, and then I'm going to call this one radius 2, because radius 1 is less than radius 2. They're not equal. Radius 1 again is just from the center out to H, where radius 2 is from the center out to F. They're not congruent radii, therefore the arcs are not congruent. And B, now PQ is 65 degrees. RS, we're going to have to calculate. Now it's safe for us to assume that PS is the diameter. So here I'm going to need to subtract the 65 and the 50 from 180. So 180 minus the 50 minus 65 leaves me with 65. So RS is also 65 degrees. Because these have the same measure and they are in the same circle, they are congruent. So PQ is congruent to RS. And if we want to explain, because they have the same measure and are in the same circle. And then our last one here, JK, is 90. MN is also 90 because LN is a straight line. We see that this side was 90, so this side is also 90. So they have the same measure. Now we have to look at the radii. So come down here, the radius, and I'm going to do O down here, is given as 6. the radius of P, I'm given the diameter, so I have to do the diameter 12 divided by 2, which is 6. So they have the same radius, which means that JK is congruent to MN because they have the same measure. If I can spell that one, and belong to congruent circles. Okay. Are the circles congruent? We determine by the radius. Are the measures the same? We have one where the radii were not the same, the circles were not the same, so the measures, even though they were the same, are not congruent. Circles the same, measures are the same, they are congruent. Circles are congruent, measures are the same, they are congruent. This is often missed. Try to make sure you understand what's going on. Okay. Well, this wraps up our first two sections. So hopefully we're doing good and understanding things so far. If not, you know to ask.